Alright, so last video basically went through faults. We went through the types of faults and we went through some important stuff that you need to pay attention to while doing fault analysis. And we also went through the sequence of steps that you go through if you were to plot the equivalent circuit for the fault. So you have your neutral bar, your generators, then your equivalent impedance seen in between, then the location or the bus in which the fault occur, then the squiggle and the F connected. So you kind of see that applying in this question. So looking at this system we have on this side, right? So we have a two generators, we have a transformer, we have four loads, we have 4 transmission lines, and we have 5 buses. Alright, so remember, a bus is just a location where power enters or leaves, or enters and leaves. So in this bus, the power enters and it has a load in it. The bus in this case will be entering. So it's just the bus is just there to take and power to come in and leave. Right? So, and we have our generators and we have our transformers. So if we were to just run faults, so we could right click on this and go to fault. And we could do a little bit of analysis on the different types of faults. So here we could choose where the fault happens. So inline fault meaning the fault happens in the line or on the line itself. So that's basically what happened here. The fault occurred on the line, and we could put the location, whether it's 34% away from the generator or the bus, or 100% away, or 90% away, 10% away, right, at the particular bus. Or we could just put the fault on the bus itself, which in most cases is what happens, at least with the questions. In reality, the fault will happen on the line itself, because the tree falling on the line. Very rare you'll find the fault at a particular bus. Alright, so we have these. So we have the different type of faults that we went through. So you have your three-phase balance, your single line to ground, your double line to ground, and your line to line fault. So your line to line, double line, and single line are your asymmetrical faults, and your three-phase balance are your symmetrical faults. So let's say we have, or we want to run a fault analysis of a fault at bus 3. So the fault happens at bus 3. So if we were to click bus 3 and we want it to happen at the bus, so we click bus faults and we run a single line, sorry, a three-phase balance, a symmetrical fault, and we could calculate at the bottom. We'll notice that the 3 phases A, B, and C went to 0 because all the phases were shorted to ground. On top here, we could see the fault. So we have the fault currents. We could put it in per unit. When amps is the actual, the per unit, you'll need to multiply it by the current base to get it into amps. So if you have the per unit and the amps, you could always get the base. Right? So anyway, so this is the actual fault current for a fault at bus 3, a three-phase balance fault at bus 3. If we wanted to do, let's say, a single line to ground fault at bus 3, meaning one line goes to ground and the other 2 lines are unaffected, notice the fault current dropped. Let's see, line to line, fault current dropped, and well, double line to ground, the fault current increased, but it's still less than the three-phase balance. So the three-phase balance is majority of the time the most destructive of the faults. Alright, so for now we won't be going too deep into the asymmetrical faults because that's a whole topic by itself, but for now we're just dealing with the simpler one, which is the three-phase balance fault, right, which is the most destructive of them. All three phases go to ground and it has the highest fault current of the four types that we have here. Yeah, there are more types, but for now we are limited to these faults here. So let's go back. Right, so that's basically what we went through in the last video. So different types of faults. So what I want to do in this video, I'll just get back the original screen and split it again. So you want to run or do the actual calculations for faults so we can actually compare the values so you can actually see how this works in actuality. So you want to compare our calculated value with the value we get in PowerBoost. So let's do our faults, single faults, bus faults. We want to do, let's full screen it. How bus faults? Three phase. And let's do that bus 2. So we have this value. So let's keep this value in mind for future fix. So let's go back to circuits. Let's split back the screen. I do some maths. So the first thing we do is we have to follow our steps to the neutral bar. So we just draw the neutral bar. Neutral. So it has check. Then we draw our generators. So we have two generators. We have this generator up here, and we have this generator down here. Right, so this generator goes to bus 1. So we have a generator, and this going to bus 1. And then we have another generator, and that going to bus 5. Yeah. Then, just keeping it simple for now, we're not adding any impedances and stuff as yet. So the other step would be after added generators, the equivalent impedance we wouldn't know as yet, but the trick is to draw the bus location or the location of the bus. Just draw it at the bottom of the bar and then put the fault F, and here's what you're gonna do. So this happens at bus 2, just here. So then you're gonna basically connect the other buses and it will naturally go to bus 2. So watch it. So let's say we start at 1. So 1 going to 3. So we know we put a bus and put 3. So let's not draw it that big because we're not sure how much space it will take up. So 1 going to 3. So we could probably put 3 right here. So 1 goes to 3. So that's that there check. Then 1 also going to 2. So this case, this 1 here going straight down to 2. And that is where the fault happens. So we did this line here, and we did this line here. So this is 3. So now 3 go into 4. So we have to draw another line and put the connection to 4. Alright, and then 4 go into 5. So draw the connection to 5. And then 4 going straight to 2. So therefore that will go straight down to 2. So did we account for all the lines? So we have a generator going to 1, check. Then bus 1 going to bus 3, so we have that. Then we have bus 1 going to bus 2, we have that. Then we have bus 3 going to 4, so yeah, 3 going to 4. Then we have 4 going to 5, cool, 4 going to 5. And what else we have? I think that's all. So we have 1, 2. So I like to count the lines. So we have 1, 2, 3, 4, 5 lines, and we have 1, 2, 3, 4, 5 lines. So we are counted for all the connections on the graph. So if you go back to our rulebook, we did the neutral bar generators, the equivalent impedance we will do just now. We did the bus location and the fault. So the trick is draw the neutral, put the generators like normal, then just draw the faulted location of the bus at the bottom, and just put this squiggly and the F mean the fault. Then when you have that now, you have the buses with the generators and you have your faulted bus. You just draw in the other buses in the middle, and you just draw the lines connecting them. That is really all it is. After that, you will know how all the connections are going. So now is where we add in the impedances between them from the diagram. In this case, the per unit impedance of the diagram. So in Powerwheel, your per unit values are already given to you at a standard MV base. So they already standardize it, so we don't need to raise it to another base. Again, everything already standardized. So after we draw this circuit, we have to add in the impedances. So I think I'll just do it right here. So let's say we want to do from 1 to 2, which is this one here. So I'll use red to signify that we did it or replaced it. So 1 to 2, which is this line, so we double click on the line. And when we double click on the line, we will see the per unit impedance already at a base. So it will be 0.012580 on it. So since we want the impedance, we have to do the square root of the real part squared plus the imaginary part squared. So in this case, it would be square root of 0.012580 squared plus 0.0481 squared. And we'll end up with, at the end, impedance connecting the two, and the value for it will be 0.049. Let's keep it to 2. In this case, 3 decimal places or 2 significant figures for now. So that will be the connection from 1 to 2. So we can do the connection from 1 to 3. Same thing. So we double click on the line to get the R and the X, and repeat the same thing. So it'll be the square root of 0.007890 squared plus 0.03692 squared. And the answer will be, so let's replace this with our impedance, and it was 0.037. Cool. And then that was this one here, and then that one there. The next one we had to do is 3 to 4, which is here. So let's erase it. So 3 to 4 we go across. Most likely it will be the same as the other one, but let's see. So 0.01. So same thing, so we do square root 0.01231 squared plus 0.0614 squared, and we will end up with 0.0626. 6, 3 in our case, because we're only going up to 2 significant figures. So that was that. So the next thing to do is from 4 to 2, which is this line here. So same thing, double click on the line, get the r and the x. So we just do square root of 0.00789 squared plus 0.03692 squared. And we get our answer. So that was 4 to 2. So that was 0.0377. Nice. And then which we want from 4 to 5. So 4 to 5, there's a transformer. So same thing, say double click on the transformer, and it should give you, well, in this case it's only x. So we get true. So the square root of that square, the square and the square will cancel. So it'll be 0. The answer will be 0.02348. So we just draw our impedance. So it was 0.02348. And then the last thing we have to do is the generators themselves has an internal impedance to it. So to do that, you just double click on the generators, and you should be able to get the positive, negative, well in this case, well we already knew all that. So yeah, the internal sequence impedance, so is 1 to the square root of 1 squared will just be 1. That's all that there. So you go down to false, and positive is 1. So it'll be 1 for the impedance. And well, for the top one, same thing, you double click on it and go across the faults. So both of them were 1, or both of them are 1. So we just go back to the diagram and erase. And you just add the generator, but just put a impedance after it. Yeah, so I think we could go ahead and do so. Come down, generator, impedance 1, generator, impedance 1. Right, so that will be the completed circuit with the impedances with respect to our faults at bus 2. So the next thing we will do in the other video is reduce the circuit to get the actual fault current and MV short circuit value for the fault at bus 2, and we'll check to see if we got something similar to what Power will had. Alright, so see you next one.